Chapter 3, Module 1. The purpose of this module is to refresh our basic knowledge of set topology which we require in this course. We start with defining a continuous function and then we state certain facts about continuous functions. Finally, we prove what we call testing lemma for continuous functions. In what follows, we shall denote topological spaces by x tau, y sigma or simply by x, y, etc. Now, a function will be denoted by simply f without mentioning its domain or codomain. Now, a function is said to be continuous if f inverse u is in tau whenever we start with u from sigma. That means, if a function pulls back the open sets of the codomain to the open sets of the domain, then the function is called continuous. A function is called an open map if it takes all the open sets of domain to the open sets of the codomain. A function is called a closed map if it takes closed set of x, the domain, to the closed set of y, the codomain. Now, we define what is called a homeomorphism. A function f from x tau to y sigma is called a homeomorphism if f is 1 1 on 2, continuous, and f inverse is also continuous. Now, the following are obvious examples of continuous and open maps. The first one is, if we take any function whose domain is a discrete space, whatever be the codomain, the function will be continuous. Any function from an arbitrary topological space to indiscrete space is always continuous. Any surjective function from an indiscrete space to any topological space is an open map. Any function from an arbitrary topological space to discrete space is an open map. Any constant map is always continuous. Now, we state without proof several equivalent conditions for a function to be continuous. Suppose f is a function from x tau to y sigma, then the following statements are all equivalent. The function f is continuous if and only if for every closed set in y, f inverse k is closed in x. That is, if and only if to for each point x in capital X and any neighborhood w of f x in y, there exists a neighborhood v of x such that f v is contained in w. For every a subset of x, f of closure A is contained in f of a whole closure. It is equivalent to, for every b subset of y, the closure of f inverse b is contained in F inverse closure of B. It is again equivalent to for each x of capital X and for any neighborhood W of f x, F inverse W is a neighborhood of X. If script B is a base for sigma, then F inverse B is in tau for all B belonging to script B. If script S is a subbase for sigma, then F inverse S belongs to tau for all S belongs to script S. Now, G and H are equivalent to continuity of the function f, means that we may not check whether all the open sets of y are coming back to the open sets of x. It is enough to check the result for if S is a subbase for sigma, then F inverse S belongs to tau for all S belonging to script S. Now, we see that the equivalence of condition A, condition G and condition H says that for continuity of the function f, we may not check whether all the open sets of y are pulled back to the open sets of x by f or not. It is enough to check whether the subbasic members of y are pulled back to the members of tau. Finally, the last equivalent condition in this list is F inverse of interior B will be contained in interior of F inverse B for all B subset of y. Now, we prove a simple result that if f is a continuous function from x to y and g is a continuous function from y to z, then the composite function, that is g composed f, which is from x to z, is also continuous. Let us take V, an open set from Z. To show that G composed F inverse of V is open in X. Now, we see it is just a set theoretic checking that G composed F inverse of V is actually equal to F inverse of G inverse of V. Now, since G is continuous and V is open in Z, G inverse V is open in Y. Now, the continuity of F implies that F inverse of G inverse V is open in X, and so by the equality G composed F inverse of V is equal to F inverse G inverse V, we can conclude that G composed F is a continuous function. We also have that whenever we restrict a continuous function to some subspace of a given space X, then it will be continuous. So, we state the theorem properly that if f is a continuous function from x to y and S is a subset of x such that S induces the subspace topology from x, which we denote by tau s, then the restriction function f on S from S to y is continuous. Now, let us take V, an open set from y sigma. Now, f restricted to S inverse of V is equal to all the points of S such that f restricted to S maps the point x inside V, but f restricted to S at any point x of capital S is the same thing as f x for all x in S. Hence, f restricted to S inverse of V is equal to S intersection f inverse V. Now, since f is continuous and V is open in y, f inverse V is open in x. And so, by definition of subspace topology, S intersection with f inverse V is an open set in S tau S. Consequently, by the equation 2, that is f restricted to S inverse of V equal to S intersection of f inverse V, we can conclude that f restricted to S inverse of V is open in S tau S, proving the continuity of f restricted to S. We now prove a result called pasting or gluing lemma, which states that under certain conditions more than one continuous functions can be glued together to form a continuous function. Now, the statement of pasting lemma is, if we start with a topological space x tau and we know that A and B are closed sets in X such that capital X is equal to A union B, we know two continuous functions f and g. F is a function from A to y and g is a function from B to y, where y is another topological space. Then, whenever we take a point x from A intersection B, it is also known that f x is equal to g x. In these circumstances, if all these conditions are satisfied, then there exists a continuous function h from x to y such that h restricted to A is f and h restricted to B is g. Now, we prove this theorem. We define a function h from x to y by this. Whenever x is taken from the set A, h x is equal to f x, and whenever x is taken from B, h x is equal to g x. Then certainly h is well defined, because whenever the point x is taken from A intersection B, h x is equal to f x as well as g x, but that is true by the given condition. Also, h restricted to A is equal to f and h restricted to B is equal to g. To show that h is continuous, now let us take any closed set from Y. then H inverse k is actually F inverse k union G inverse k. Now, since F inverse k is closed in A and A is closed in X, F inverse k is closed in X. Similarly, G inverse k is closed in X, and so H inverse k being union of two closed sets is a closed set. Product of topological spaces give method of construction of various other topological spaces from given ones. Now, we shall introduce finite product of topological spaces and see one or two examples of such product of spaces. Suppose we take two topological spaces, one is x tau and the other one is y sigma. We want to define the product space x cross y. For that, we take the Cartesian product of x with y, that is the set consisting of the pairs x comma y such that x varies over capital X and y varies over capital Y. We take tau cross sigma as the collection of all sets of the form u cross v such that u is an open set of capital X and v is an open set of capital Y. Then we see that empty set and x cross y, that is the whole set, both are inside this collection. Whenever we take two members from tau cross sigma, one is u1 cross v1, the other one is u2 cross v2, then u1 intersection u2 cross v1 intersection v2 is again in tau cross sigma. Now, since tau is a topology, u1 intersection u2 is a member of tau and v1 intersection v2 is a member of sigma, thereby showing that tau cross sigma is a base for some topology on x cross y. This topology formed by taking this collection as base is called product topology on x cross y. We cite a few examples of product spaces up to homeomorphism. We take the example of a cylinder. Cylinder is a three-dimensional object described by the set C, which consists of the points x, y, z in R3 such that x square plus y square equal to 1 and the third component z varies inside the closed interval 0 1. Now, then C is actually homeomorphic to the set S1 cross the closed interval 0 1. How do we prove it? First, we consider the map F from R2 cross R to R3 given by F ordered pair x y comma z is equal to the triplet x y z. This is actually a homeomorphism which can be verified easily. Now, if we restrict F to S1 cross 0 1, then the restriction map becomes the desired homeomorphism. Now, let us take the example of a torus. We show that torus is a product space of S1 with itself. Now, what is a torus? Torus is once again a three-dimensional object which looks like a tire. Mathematically, the torus is the collection of all points x, y, z of R3 such that x square plus y square plus z square minus 4 times root over x square plus y square equal to minus 3. Then, if we define a map F from S1 cross S1 to the torus T2 described by F of the pair xy comma the pair x dashed y dashed is equal to the triplet x dashed plus 2 times x, the second component is x dashed plus 2 times y and the third component is y dashed. Then it can be checked that this triplet satisfies the condition of the torus, and it is not hard to see that it is again a homeomorphism, because if you take the map G from T2 to S1 cross S1 described by this formula that G x y z is equal to the pair with the first component as x by root over x square plus y square comma y by root over x square plus y square and the second component as root over x square plus y square minus 2 comma z, then this G is an inverse of F. So, since the function f is invertible, it is a bijection, and the nature of the function, the description itself says that the function is continuous. Also, the nature of the function g says that g is also continuous. Hence, S1 cross S1 is homeomorphic to T2. So, we can view a torus as a product space of S1 with itself. Finally, we state a very useful result that we shall use throughout our course. Consider the projection maps P1 and P2. That means, we are taking the function P1 from x cross y to x, which takes the pair xy to the first component x, and the function P2 from x cross y to y, which takes the pair xy to the second component y. It can be seen very easily that P1 and P2 both are continuous functions, they are open functions and they are both surjective. Now, if f is a function from z to x cross y, where z is any topological space, then the continuity of the function f follows from the continuity of the composition Pi composed f for every I equal to 1 and 2. Now, this is a very important result that we are going to use without any mention. Now, in fact, all these results are valid for any product of spaces, not necessarily finite. The definition of arbitrary product of spaces needs a little more care and have not discussed here, because we do not need these concept of infinite product in our course. We end this module with a note that the properties we have discussed here are those which we require to develop our course.